In this video, we're going to discuss significant figures. As you know, being able to assess uncertainty in experimental results and in calculations is very important in science. So I'd like to review significant figures as well as how we use significant figures in calculations. This will be helpful for when you're submitting answers in your courses for assignments and for examinations. So first of all, what are significant figures? These figures include all certain digits and the first uncertain digit. And there's always some uncertainty in the last digit of an experimental value or a calculation. Significant figure rules are guidelines, and they do not always predict the correct number of significant figures. However, we use significant figure rules as a shortcut so that we do not have to do a detailed error analysis on everything we calculate. So let's first look at the rules for counting sig figs. There are 5 different rules that we should consider. The first is that all non-zero digits are significant figures. The second is that leading zeros are zeros that precede all the non-zero digits. These do not count as significant figures. Captive zeros are zeros between non-zero digits, and these are always counted as significant figures. Trailing zeros are zeros at the right end of the number. They are significant when there is a decimal point in the number. Trailing zeros are not significant in numbers without decimal points. And lastly, exact numbers are considered to have an infinite number of significant figures, but they are often not reported. They are not obtained using measuring devices, but are determined by counting or by definition, like conversion factors. They do not impact the number of significant figures in the result of a calculation. For example, when you're converting temperatures from Celsius to the Kelvin scale using a conversion factor, this conversion factor can neither add or subtract the number of significant figures from your experimental result. So let's look at some examples. So if we start with our non-zero integers, if we have the number 511, we know that we will always count all non-zero integers, and so we would have 3 sig figs in this particular value. Captive zeros, again, these are zeros that are between non-zero digits. So for example, if we have 1008, this would be 4 sig figs. Similarly, if we had 1.008, this would also be 4 sig figs. Trailing zeros. So with trailing zeros, if we had the number 100, because there is no decimal place in this number, this would only be equivalent or only contain 1 significant figure. However, if we were to place a decimal at the end of this number, we would consider this to contain 3 significant figures. Similarly, if we had trailing zeros for a number as shown, this would also be equivalent to 3 sig figs. And finally, for exact numbers, these again are numbers that are not obtained using measuring devices, but are determined by counting or definition. So for example, if we were to carry out 3 experiments, the number 3 would be considered an exact number, and therefore would carry infinite number of sig figs. And so when using this particular number in a calculation, let's say an average, this would not be used to determine the number of sig figs in your final result. Similarly, if we had conversion factor as 1 gram, is equal to 1,000 milligrams, neither of these values would be considered in the rules of operations using sig figs. They are considered exact numbers and therefore carry an infinite number of sig figs. Now let's look at the rules for determining the number of significant figures in operations. So when performing operations with values with different degrees of precision, the precision of the final answer can be no greater than the least precise measurement. In practice, it is a good idea to keep one more digit than is significant during the calculation to reduce rounding errors. So that would be the second uncertain digit. However, when you express the final answer, it must be expressed with the proper number of significant figures. So again, in practice, you can carry one additional digit beyond what's considered a significant figure to help reduce rounding errors. But you shouldn't be carrying all the digits that are shown on your calculator. That can lead to confusion in terms of what the number of significant figures should be in your final result. So in addition and subtraction, a sum or difference cannot have an absolute precision greater than that of the least precise number used in the calculation. The number of significant figures is not determined by the number of significant figures in the measurements. For multiplication and division, a product or quotient contains the same number of significant figures as the measurement with the least number of significant figures. The number of significant figures in the answer is determined by the measurement with the least number of significant figures. So let's look at some examples of that. So if we were to calculate 99.1 plus 1.1543, the sum of these two values would be 100.2543. Now the least precise measurement is 99.1, so that will dictate the number of sig figs in our final calculation. And so our final calculated result, if we were to express this with the correct number of sig figs, would be 100.3, one decimal place being shown. Now, if we were carrying this calculation somewhat through, in some larger calculation, carrying it through, and we weren't expressing our final answer, the way that you should show this in your calculation would be, the result would be 100.2 and then subscript 5 to indicate that you're carrying that 5 as the first non-significant figure or the second uncertain value, depending on how you want to look at that definition. Now for multiplication or division, again, the number of sig figs in the result is the same as the number in the least precise measurement used in the calculation. So if we were to look at this example, 99.1 divided by 1.11, the result of this calculation would be 89.19891 and so forth. Okay, this would be what you would see from a calculator. Now, based on the number of significant figures in the numerator, 3, denominator, also 3. So 3 will be found in our final calculated result. And so the final answer would be 89.2, expressing the 3 sig figs. Now, if this were part of a greater calculation, you were carrying this through before expressing your final result, you could carry this through as 89.1 subscript 9. And that would be fine to carry that to one additional digit that's not considered significant. And the subscript identifies that to the reader, that you're not considering that a significant figure, but you're carrying that through to help with potential rounding errors. One last point is that, yes, there's an 8 that follows that value, or that digit 9. We don't round that up any further. We just express the digit that is one past the number of sig figs in your result. Now, the rules for determining the number of significant figures in logarithms, both common and natural, and anti-logarithms are as follows. For logarithms, when calculating the logarithm of a number, keep as many significant figures to the right of the decimal point in the resulting number as there are significant figures in the original number. So for example, if you're taking the log or ln of a number that contains 4 sig figs, then the resulting number, your calculation, should have 4 sig figs to the right of the decimal point. For anti-logarithms, so when you're converting the logarithm back into the corresponding number, we use the same rules. So the number of significant figures in the mantissa, that is the number of sig figs to the right of the decimal place in the logarithm, this gives the number of sig figs in the resulting number. And so we'll go over a couple examples of that in just a moment. Now I want to note that it is very important to explicitly show the numerical value of the exponent before calculating the anti-logarithm. So if you have e to some quotient, you must calculate out the resulting value of that quotient before taking the anti-logarithm. Otherwise, it becomes very difficult at the end of your calculation to assess how many sig figures you should have in your final response. So do not leave a complex product or quotient of numbers. Again, otherwise the number of sig figs in the resulting number may be incorrect. So let's look at a couple examples of logs and antilogs, lns and e to the x. So if we look at an example, let's take the log of a number with 3 sig figs, 0.00722. The calculated result would be minus 2.14146. Now there are, again, 3 sig figs in this value. So when we take the logarithm of this value, we should express our resulting number as containing 3 sig figs to the right of the decimal place. And so our final result would be minus 2.141, which expresses those 3 decimal places, or 3 sig figs to the right of the decimal. And so that would be the resulting value for this logarithm. So in conclusion, when you take the log of a number with n significant figures, the result should have n decimal places. And the number in front of the decimal place, this indicates only the order of magnitude. It is not a significant figure. Now the rule for natural logs, that is ln, is similar. It's not quite as clear-cut, but for simplicity, we will use the same rule for natural logs as well. So for example, if we take the natural log of 0.0056, our calculator may show minus 5.1850. And again, there are 2 sig figs in the natural logarithm, and so we'll show 2 decimal places in our final result. So this would be equal to minus 5.18. Now going the other way, the opposite of taking a log of a number is to raise 10 to the power of that number. And so the significant figure rule for this function is the opposite for the sig fig rule for logs. So let's look at an example. If we had 10 to the power 2.890, our calculator might say 776.25. Now there are 3 significant figures to the right of the decimal place. So when we take the antilog, our final calculated result will also contain 3 sig figs. And so our final result should be expressed as 776. The same thing for natural logarithms, base e. So if you have e to the minus 2.55, if we were to calculate that, we would end up with a string of numbers of 0.078082. Now, again, there are 2 sig figs to the right of the decimal place, and so our anti-natural logarithm would be, our final result would be 0.078. So 2 sig figs to the right of the decimal place, 2 sig figs in our final result. So to conclude, when raising 10 to a power, if the power of 10 has n decimal places, the result should have n significant figures. And the rule for raising e to a power is similar. So for simplicity, we use the same rule for both situations. So again, it's also important to remember that when you express your exponents, that you don't express these as quotients or products. It's really important to express the final result. And I always generally recommend that you show all these values not using scientific notation. When you're using scientific notation to represent the exponent, determining the correct number of sig figs can be a little problematic. It's much easier if you represent the value in this way, which shows the number of sig figs with a certain number of decimal places. Now, for numbers in scientific notation that carry a negative exponent, so let's say 2.40 times 10 to the minus 1, those generally work out quite fine, that the number of sig figs in the value preceding your 10 to the negative power, that will be the number of decimal places that you use to determine the number of sig figs in your final anti-log or anti-ln. But when that exponent is a positive value, these are very large numbers, or e to that number becomes a very large number. And so the significance becomes a little bit tricky to determine. So in those scenarios where you have very large values, we'll maintain that we carry at least one significant figure. We still want to report that calculated value. So we'll keep at the minimum 1 sig fig, obviously. We're not going to not calculate that anti-log or anti-ln. Nonetheless, I would recommend that you don't use scientific notation when expressing the exponents. It'll make it much easier for you to determine how many sig figs in your calculated result if you show the number of decimal places that contain significant figures. So the rules for rounding significant figures in an answer. When a value contains too many sig figs, it must be rounded off. Now, there are two methods that are commonly used to minimize the error introduced into a value due to rounding. And of the two methods, method 2 is the method that I would like you to use in your calculations this semester. But I'll go over both methods for your information. So method 1, this is a more common method when we first learn about rounding. And this involves underestimating a value when rounding the 5 digits 0, 1, 2, 3, 4. And overestimating the value when the rounding of 5 digits 5, 6, 7, 8, 9. With this approach, if the value of the digit to the right of the last significant figure is smaller than 5, we drop this digit and leave the remaining number unchanged. So for example, 2.794, this becomes 2.79. If the value preceding the digit to the right of the last significant digit is 5 or larger, we drop this digit and we add 1 to the preceding digit. Thus, 2.795 becomes 2.80. And this is the most common method used in rounding, but there is a better way to round your final result, and that's by following method 2. So in method 2, this method takes into account that 0 does not really require rounding. And when rounding 5, this value is exactly centered between the underestimated value, if it is rounded down, and the overestimated value, if it is rounded up. Therefore, 5 should be rounded up half of the time, and it should be rounded down half of the time. Since it would be difficult to keep track of this when performing numerous measurements or calculations, 5 is rounded down when the preceding significant digit is even, and 5 is rounded up when the preceding significant digit is odd. So values less than 5 are rounded down, and values greater than 5 are rounded up. So for example, 2.785 would be rounded down to 2.78, and 2.775 would be rounded up to 2.78. So for this semester, I would like you to use method 2 when rounding significant figures in a final answer. So if you have any questions about counting significant figures or using significant figures in various operations, or for the rules of rounding significant figures in a final answer, by all means, send me an email. Thank you.